From the colleges and universities of the nation, CBS Television brings you The Search to know and understand man and his world, the search for a richer, happier life for all.
I'm Charles Romine. This is a report on a revolution in machines. This is Professor Donald B. Campbell of the Massachusetts Institute of Technology, a leading authority on automatic machines and processes. For the next half hour, Professor Campbell will be our guide as we take you on a cross-country tour of laboratories and plants that are pioneering in the development of new robot machines. Right now, we are in the North Grafton, Massachusetts plant of the Wyman Gordon Company. Professor, what is that mammoth machine right over there?
It's called the Big Squeeze. It's one of the two largest hydraulic presses in the United States.
What do they use it for?
They forge aluminum parts for airplanes and magnesium parts. It squeezes the metal together like so much cookie dough. The total pressure is about 18,000 tons. That's 36 million pounds.
Wow, I never would have believed it. I guess that represents the revolution in machines, bigger, more powerful machines.
No, that's not quite right. These new mammoth machines, for all their force, don't do anything except be perhaps more efficient than old machines did. For all their power, they are simply a replacement of man's muscles. The important thing to keep in mind is that all of these machines are performing purely mechanical functions. They are the dinosaurs, the apes, the Neanderthal men in the world of machines. Big Squeeze here is just another one of them. It's simply bigger. But recently, an important change is taking place in the machine. An important and big change. Machines are going through an evolution. They are becoming more than merely muscles. Now let's go back to MIT and see how these machines are evolving.
All right. What on earth is that?
Why, that's Felix.
Felix, what is he, a pet or a mascot here at MIT?
Well, you could call him a pet at the Institute. He doesn't greet everybody that way. In fact, he's not greeting you at all. He's just looking for some sunlight. Felix is a device that shows how a machine can take over one of the human senses, vision. He is a machine that represents an advance in evolution. Oh, there's Professor Wiener. Professor Wiener is an internationally famous mathematician who supplied many of the basic ideas that allowed this field of automatic control to develop.
How do you do, sir?
I've just seen an amazing demonstration out here, and I'd like to ask you a couple of questions about it.
Sit down.
Fine. Just a moment ago, I saw a demonstration of an amazing machine, Felix the Moth. Well, now, did you build Felix as a toy or as
Most
a showpiece?
certainly not, as a demonstration piece. He's been jazzed up for movie purposes and had a certain amount of beauty treatment, but he's fundamentally an instrument to examine how such machines behave.
What kind of a machine really is Felix?
Well, Felix is primarily a hastily put-together show machine to show what one can do with automata these days of a very different sort from the old-fashioned automata of the 18th century. You know those figures that dance around on the top of a music box. Has it ever occurred to you that they're blind and stupid? That is, they go through a set pattern and they don't perceive anything, and nothing that happens outside will change what they do. Well, Felix is different. First, he isn't blind, and second, he's got something that you can call a crude brain. Now, when I say he isn't blind, he's got a very curious sort of an eye, or pair of eyes. He isn't made to see images, but he is made to perceive light. A lot of the primitive animals have eyes like that. But in addition to that, he balances the light for the two eyes, and the change in balance, the light is collected by photoelectric cells, moves a rudder that steers him toward the light.
What about the other senses, Dr. Wiener? Are you building in other human senses into these new robot machines?
Well, let's take hearing. We have already guided missiles, that is, sonic torpedoes, that chase after the sound of a ship.
Would you say that machines are becoming smarter and smarter?
Yes, we're making them smarter and smarter. We're building into them better memories. We're building into them the possibility of learning. And those things are happening very fast.
By that, do you mean that we have machines that actually think?
The word think is one of the words like life and so on, and soul, which are bad words. They mean just what we want them to mean. But I would say that we have machines which, if they were to be for the first time discovered by an animal psychologist, would be said to think in the way that animals do, yes.
We're now reporting from the Digital Computer Laboratory at MIT. With us is Jay Forrester, director of the laboratory. Mr. Forrester, what part of the laboratory are we in right now?
This is the control room for the Whirlwind digital computer.
Is this the entire machine right here?
No, the Whirlwind computer itself is in the room next door.
What's Whirlwind used for?
Whirlwind is used for scientific and engineering research and for studies on various military problems. It's one of the most versatile and fastest machines that's been built, and will carry out about 25,000 arithmetic operations a second. To give you an idea of the speed, let's consider multiplying together two numbers. Take, for example, 31946 multiplied by 27189.
Boy, that was a very short fraction of a second to get that answer.
Well, you see, in 15 minutes, Whirlwind can carry out the solution to a problem that would take a person at a desk calculating machine 15 years to do.
Tell me, how does Whirlwind compare in regard to making errors with us humans?
Well, it might give you an idea if you would consider one of these multiplications as equal to dialing a phone number, and then realize that the machine makes an error only as frequently as would be equal to people dialing one wrong phone number in this country every 2 years.
How does it communicate its answer to us?
Well, Whirlwind has several ways of communicating with us. One way is to record information on those rolls of magnetic tape over there. And when it's finished with a problem on tape, the tape is used to control the typewriter on the other side of the room, and that gives us a page of printed information. Whirlwind also can record engineering curves on a cathode ray tube face, something like a television set, and this gives us plotted results that are easier to understand than a page of numbers.
Well, after watching Whirlwind in operation, it seems it has a high degree of mental activity. Now, would you call that electronic thinking, Mr. Forrester?
Well, I'd be careful about the use of the word thinking. After all, a machine like this only carries out the instructions that men prepare for it.
Well, now we've seen machines with brawn and machines with senses, and right here, machines that almost think. Is the next step of putting them all together?
Not quite. I think we have the important field of control that you ought to look into.
Dr. Brown, I understand that you are the head of the electrical engineering department, and I'd like to ask you a question or two. We've just seen the electronic brain at Mr. Forrester's laboratory, and I'd like to know, what can these electronic brains do other than remember, obey orders, and so on?
These brains, these memory devices, can perform very clever functions when they are made part of automatic control systems, but only provided these automatic control systems have the feature that we like to call feedback.
Feedback. Now, that's a very interesting word. What exactly does it mean? What is feedback?
Well, I would like to explain feedback to you in terms of a very simple, very commonplace, everyday experience. Now, supposing that we assume that we are in a schoolroom. We have a text and we have a teacher. And the teacher knows what the text has in it and what the student is supposed to learn. Now, if there is no feedback, the teacher has a very poor way of telling whether the student understands. This is why, in schools, our children are required to take a quiz, because it is by means of the quiz that the teacher can tell how well the student understands. It is the feedback feature by means of the quiz that makes our educational process even partially effective. But outside the classroom, feedback can perform a very important function in mechanisms, because it is by means of feedback that automatic control machines can perform self-regulating operations.
Do you mean by that at certain situations, these machines can react all by themselves?
Oh, certainly. They certainly can. And let me show you a model of a device that we find frequently on our ocean-going liners. Now, we have here an experimental rig that is intended to show how a vessel might steer itself. Shown forward of the mast is a gyro compass, and assume that the vessel changes its direction by a degree or so.
Such as would happen in heavy seas with strong winds, I suppose.
That's right, exactly. Now just watch. As it moves off course, the gyro compass picks up information, gives the signal to the steering motor. The steering motor, in turn, will control the position of the rudder. Then, if the vessel were in the water and able to move, as it moves forward, it would come back onto course, and the gyro compass would cancel out the signal.
Oh, so that's why it's called feedback, because it feeds back the information necessary to correct itself. Is that right?
Exactly. The gyro compass detects and continuously monitors the desired heading. And whenever it detects an error in the desired heading, it gives the instructions that will permit the ship to correct itself.
That's pretty ingenious.
Oh, ingenious, but rather commonplace. Now, feedback in weapons plays a very vital role. Feedback is found in many places throughout the device. In the top-secret guided missiles, the radar signal is the feedback link to the nervous system of the missile that tells the nervous system whether it has aimed the missile in the direction that will permit it to destroy the target.
Now, I've seen machines that are muscle machines, sense organs, electronic brains, and have feedback. Now, tell me, is this the ultimate in what you can put into a machine? Is this the ultimate machine?
Well, sir, here you've raised the $64 question that interests all people interested in control. I would rather say that we have developed some rather clever machines. They are valuable and useful machines, but we have a long way to go before we will have developed an automatic machine that can replace the human being. Our machines today are simple. They really cannot think. But we are making some progress in the direction of learning what we might be able to do to machines in order that they do some elementary thinking. And I would suggest that you go and have a talk with Dr. Claude Shannon at the Bell Telephone Laboratories, for I consider him one of the leaders in studies of this general character.
And Dr. Shannon, we understand that you've made many highly important contributions to the science of communications, and that right now you're working on some machines that learn. Now, I presume that this could be one of them. Is this an experiment of yours that looks very much like a little mouse? Is it a mouse?
He's not a real live mouse. Actually, it's a little mechanical mouse, which is controlled by a small computing machine. One of the classic experiments of psychology, as you know, is that of putting a mouse, that is a live mouse, in a maze and seeing how long it takes to solve the maze. What we have here is an attempt to simulate this type of behavior by means of a computing machine. In other words, to build a machine which will solve problems by trial and error and then remember the solution after it's found it. You see, the maze can be changed by moving the partitions around in any way that you choose. Perhaps you'd like to present a new problem to the mouse by rearranging the partition somewhat.
All right, I'll try and confuse him a little. I think I'll move this one right over here, and perhaps this one No, this one here. I'm almost as confused as the mouse, I think. And this one right here. How's that? Do you think that'll confuse him?
Well, let's try it and see. Suppose that I put the mouse down in this square to start with. Now, the way you set this up, it'll have to go around this path, through here, around here, and back to this brass knob in the corner, which, of course, represents the cheese. Just for fun, why don't you take your watch and time it and see how long it takes him to find his way to the goal?
Okay, we'll clock him. "52 seconds.
Yes, he made quite a number of mistakes. Why don't you put him down on the same starting point and see if he's learned anything?
All right, we will. "17 seconds. That's pretty amazing. How did he do it?
Well, like all these computing machines, it's rather complex. Actually, the brains of this mouse are down underneath the panel. Let me show you the inside of the machine. Actually, the mouse here is a permanent magnet. It's pulled around by this electromagnet here, which can move on wheels underneath the cover of the maze. The electromagnet, in turn, is driven by two electric motors, which are controlled by a miniature computing machine.
Well, one thing I'd like to know is why the first time did he make every conceivable mistake, or it seems so, and the second time went through with no trouble?
Well, part of the computing machine consists of a bank of about 50 relays, which act as a memory for the machine. When the mouse goes through the first time, it locates the partitions, makes a mental note in these relays of the positions of these partitions. Second time through, it avoids all the mistakes it made the first time.
Well, now, what do you expect to discover with devices like this?
Well, machines of this general sort are very similar to the type circuits we use in our automatic telephone work. By exploring the possibilities here, we hope to improve telephone service. Further, we hope to possibly learn something about the general design principles of machines that learn. And if we're lucky, maybe we'll learn something about that most remarkable learning machine of them all, the human brain.
We're back at MIT in the Servo Mechanism Laboratory. Professor Campbell, what's the next stage in our evolution of machines?
We can combine electronic brains with machines that do useful work. Combine brains and brawn. Mr. O'Mine, Mr. McDonough.
Hi, how are you?
Mr. McDonough and Mr. Pease, a former professor at MIT, worked together on the research and development of this machine.
Oh, well, you're the one to ask, Mr. McDonough. Exactly what does this machine do?
Well, this is an automatic milling machine. It makes many parts, such as the forming dies that are used in the manufacture of aircraft and by other industries. It often does in a few hours what it takes a skilled machinist several days to do. It's controlled by the computing machine, which you might call an electronic brain. Here is where the machine is receiving its instructions. You'll recognize the tape as being similar to that that's used at the Whirlwind machine. The metal pins come up through the tape and actually feel the pattern of holes. Now over here, we have the electronic equipment that actually controls. The first panel controls the motion of the table. The second panel controls the motion of the tool up and down. And the last panel controls the motion of the tool in and out. All of these are to a precision of 1 or 2 thousandths of an inch.
Does this machine perform all those operations automatically?
Yes, it reads the list of numbers that were recorded on the tape and performs the machine operations in the proper sequence. Right now, the holes on the tape are telling the machine to spell out CBS TV.
Now, does this give us an idea of what we can expect in the future?
Yes, several industrial firms are now building equipment of this sort, and other plants are visiting us to find out the technique and learn about it.
Well, I suppose the automatic machine represents the peak of machine evolution. It's a complete robot. That's what you're for, isn't it?
Well, we're not after the kind of automatic machines you read about in science fiction tales. We want a more sophisticated kind of automatic machine, a kind of machine that is a complete production and service system, an automatic machine, an organism, a community of machines, a combination of instruments and automatic machinery. And of course, the ultimate in this will be when men do not control the individual machines, but when instead they control complete arrays of machines arranged into complete automatic production plants.
A sort of automatic factory, is that what you mean?
Well, you could call it that.
Are there any such factories in existence today?
Certainly. At a Ford Motor Company engine plant, they have automatic machines that can turn out whole cylinder blocks with a minimum of human control. There are also automatic machines that can grind crankshafts to predetermined dimensions.
Now, isn't this just the very thing that brings about this feeling of fear of machines, the feeling that factories of the future will run themselves, that people won't be needed, that we'll be unused and useless?
You know, that's a question I believe you ought to ask the president of MIT, Dr. Killian.
I feel that we have nothing to fear from the use of new machines, provided we use them understandingly and in a benign manner.
Well, do you mean to say, Dr. Killian, that automatic factories will employ just as many people as present-day factories do?
I think that they will perhaps employ more when we consider their impact on other kinds of industry in this country. The history of technology and industry has been that it has tended to increase employment over the long period rather than to decrease it. Certainly there will be disruptions from time to time. There will be shifts in the kind of work that people do. There will be changes in industry. But I am certain that in the long run, new technology of the kind that you've been demonstrating here will result in better employment and more employment in the United States.
What will be the result of the automatic factory in reference to the worker?
This new breed of machines will unquestionably require a new breed of professional man, a new breed of engineers. We will require men who not only have a profound education technically, but who have a breadth of education that enables them to understand the social forces created by the machine. This, of course, is where the universities come in, where an institution such as MIT has a very great responsibility. We must make sure that in preparing men to undertake professional responsibilities in the age of automatic machines, that we must have an educational program that will give them a breadth of understanding of social forces, that will, in the words of Norbert Wiener, help them contribute to the human use of human beings.